Hello, and thank you for attending this presentation. My name is Angela Barai, and I am affiliated with the Faculty of Engineering, University of Rijeka in Croatia and the Canadian Institute of Technology in Albania. This work was conducted in collaboration with Jonathan Lerga from the Faculty of Engineering, University of Rijeka. In this presentation, I will discuss our paper titled Performance Analysis of Field-Level Encryption on Structure-Sensitive Data Using the Elliptic Curves. Elliptic curves, or as widely known ECC, is used in modern security systems for secure communication, digital signatures, and key exchange protocols. While its performance has been extensively studied in traditional cryptographic context, its behavior when applied to structured sensitive data in database systems is less well understood. This study investigates whether data-level characteristics of database attributes influence ECC encryption performance. To begin, I would briefly discuss the motivation behind this work. Structured databases store data with highly diverse properties. For example, credit card numbers are fixed-length numerical values. Email addresses are variable-length strings containing letters, numbers, and/or special characters. Financial balances, on the other hand, are numerical values with relatively lower entropy compared to the credit cards. These structural differences could theoretically influence cryptographic processing. However, most ECC performance research evaluate algorithms without considering the structure of the underlying data being encrypted. This actually motivates the central research question of this study. Do attribute-level characteristics actually influence ECC encryption performance in database systems? To begin with, in modern security architecture, sensitive data store data in databases most often encrypted directly at the attribute level. Examples here could include the financial records, the personal identifiers, and the authentication information. Many systems implement field-level or selective encryption, where only the sensitive attributes are actually being encrypted. However, encryption inevitably introduces computational overhead. If encryption performance depends strongly on data structure, database systems may require complex data-aware encryption strategy. But if encryption behavior is largely independent of attribute characteristics, then encryption policies could be simplified. Understanding this distinction is therefore important for secure and scalable database systems design. Existing ECC research primarily evaluates performance in traditional cryptographic contexts such as the key exchange and the digital signatures. At the same time, research on database encryption typically focuses on security models and policy enforcement. However, the interaction between the structured data characteristics and ECC execution behavior remains, again, largely unexplored. This study addresses this gap by evaluating ECC performance directly on structured database attributes. The experiments for this study were designed to isolate three main factors that may influence encryption behavior. First is the structural properties of the database attributes. Secondly, the dataset size, which allows us to study database encryption scalability as well. And the third one is the choice of the elliptical curves for cryptographic operations. A synthetic database was used to simulate enterprise database data while preserving privacy. The analysis in this study combines cryptographic benchmarking with feature-based machine learning analysis in order to evaluate whether attribute characteristics really influence encryption execution time. The dataset that I have used is a synthetic dataset, as I mentioned, containing 10,000 records, which is designed to emulate structured enterprise database data. Three representative attributes from the ones that I mentioned were selected, including credit cards representing fixed-length numerical data with high entropy, emails representing variable-length alphanumeric fields containing special characters, and account balances representing numerical attributes with relatively lower entropy compared to the credit cards. These attributes provide diverse structural characteristics that allow systematic analysis of encryption behavior across different data types. Two elliptical curves were evaluated for encryption benchmarking, including here the SEC P256R1 and the Brainpool P256R1, which are widely used standardized curves. Another curve, the X25519 curve, was used as a reference curve for exchange operations. Table 1 shows the average encryption and decryption execution for the evaluated curves. The results indicate that the curve SEC P256R1 consistently performs better than the Brainpool P256R1 curve. Encryption times are lower than the variability across repeated measurements, which is also produced. This suggests that the curve selection actually influences the cryptographic execution, the performance of the cryptographic execution. This figure, on the other hand, illustrates how encryption time changes as the dataset size increases. Experiments were conducted using dataset size from 50 records to 10,000 records. The results indicate a near linear increase in encryption execution time. This indicates that performance is primarily determined by the number of cryptographic operations performed rather than the structural differences in data. This predictable scaling behavior is important for large-scale database systems. To analyze further whether attribute characteristics influence encryption time, several structure features were extracted from each attribute. These include the field level, the field length, the character composition, the Shannon entropy, and the dataset size. Furthermore, a random forest regression model was used as an exploratory analytical tool to evaluate whether these features explain variation in encryption execution time. Model performance was evaluated using the mean squared error and the coefficient of determination. In this context, very low or a negative R squared indicates that attribute feature provides little explanatory power for encryption timing. This figure compares predicted encryption time from the random forest model with the actual observed value. The large dispersion confirms that weak predictive performance indicated by the regression metrics. This result reinforces an important observation. Encryption execution behavior appears to be largely independent of attribute level data characteristics, at least under the evaluated configuration. Instead, encryption is dominated by the underlying cryptographic operations, as we saw at the choice of the elliptical curve. In summary, this study provides three main findings. First, the curve selection, as I mentioned, influences ECC execution efficiency. Secondly, encryption time scales approximately linearly with dataset size. And third, attribute level characteristics such as length or entropy have minimal or limited influence on execution time within the evaluated configuration. These results suggest that database encryption strategies can prioritize curve selection and operational scale rather than complex data-aware cryptographic tuning. Before concluding, it is important to briefly highlight the limitation of this study and the direction for the future work. First, the experiment, as I explained, were conducted using a synthetic data set containing 10,000 records, but at Python-based level implementation, which may introduce additional overhead compared to optimized production environments. Future work will therefore evaluate optimized cryptographic libraries and real-world data sets. Additionally, further experiments will explore higher security elliptical curves and hardware acceleration. Thank you very much for your attention. If you have any further questions or would like to discuss this work further, please feel free to contact me at my email address or at my professor's email address, Jonathan Lerga. I really appreciate your interest in this research and look forward to future discussions. Thank you once again.